Today, we study the implicit function theorem. Firstly, we need to generalize the concept of partial derivative to vector-valued functions. Suppose U is an open subset of Rm, and V is an open subset of Rn, respectively, and we have a map capital F from the Cartesian product U and V to another Euclidean space Rp. So, and AB is a point in UV. Okay, so this is Rm, this is Rn, here is U, and here is V. So this is U plus Cartesian product of U and V. Okay, so a point AB in U V, okay, U cross V. Then given this map, then for we have a map defined on V, okay. Then this map will be denoted by F2 from V to Rp. We can define the map defined only on V. How this map is given? F2 Y is precisely F A Y. F have two variables, x and y. So we fix x equal a, just let y change. So we obtain a map depend on y only. This map is our F2. Okay. So for this map, we can talk about whether this map is differentiable at the point B or not. If F2 is differentiable, at the point B, y equal to B, then we obtain the F2. This is this is a Pn metric, right? Or can be considered as a linear map from Rn to Rp, because y values in Rn and the capital F take value in Rp. So this F2, the derivative of F2 at B is a linear map from Rn to Rp. Of course, this is simply a matrix, P by N matrix. So this F2, the derivative of F2 at B is called this to be the partial derivative of F at AB, which is by definition the derivative of F2 at B. Okay, so we have the partial derivative of our vector-valued function capital F, which is respect to a group of its variables y. Okay, of course you can also denote this by this notation. Okay, classical notation is also used. Okay, similarly, if we fix y to B, we obtain another map. Another map is F1 x is F x B. So this map, if differentiable at A, if this map is differentiable at A, of course we have the partial derivative of capital F at the point AB, which leads back to x. This is simply the derivative of F1 at A. Okay, so we have a partial derivative of vector-valued functions. Okay. In metric notation, the partial derivative of f at AB which is respect to x is an P by M matrix because our f is U V to RP. U is m-dimensional, V is n-dimensional. Okay, so F1 is a map from U to RP. Here U is m-dimensional. Therefore, the derivative of F1 at the point A is P by M matrix, which is our partial derivative of capital F, which is respect to x at the point AB. Therefore, this matrix is the partial derivative of f, which is respect to x1, xm, and here the capital F is f1, fp, because f maps into rp, it has p components, f1, fp. Therefore, these components, every fi are functions of x and y, and x is m-dimensional, y is n-dimensional, so y is fixed as b. So these are the derivative which respect to x only. So xm fp. This is the P by M matrix, represent the partial derivative of capital F which respect to x at the point AB. Okay, so we remind you that is the derivative of F1 at A. Here F1x is simply Fxb. Okay, similarly, the partial derivative which respect to y at the point AB is given by the matrix y1 f1, yn f1, y1 fp, yn fp. This is a P by a matrix. Of course, all the partial derivative are evaluated at AB, x equal to A, y equal to B. Okay, so this is the matrix representation of the partial derivative. Now, a natural question is, what's the relationship between the differentiability of capital F and the F1 and F2 we introduced here? Okay, the relationship between the differentiability of these maps. So we have this proposition. F is a map from the cross product to R. P and AB is a point in UV. Then the first result is that if F is differentiable at the point AB, then our F1 and F2 are differentiable. F1 is the map x to fxb, and F2 is the map y to fay, are differentiable. These two maps are differentiable, and the derivative is given by the derivative of capital F at the point AB, because capital F is a map from m plus n dimension to p dimensional. Therefore, F point AB is a matrix of p by m plus n. Okay, so here H is a vector in Rm and K in Rn. Therefore, the pair Hk is a vector in Rp plus n. Okay, so this vector acting by the P by M plus n matrix capital F point AB is a vector in Rp. This vector will equals the partial derivative of F which is respect to x acting on H plus the partial derivative which respect to y acting on k. Okay, the two terms in the right hand side of this equality are vectors in Rp. So their sum is also a vector in Rp. Both sides of this equality are vectors in Rp. They can be they are equal. This is a conclusion of this proposition, the first proposition. Okay, and the second consequence, the second conclusion. If the partial derivative with respect to x and with respect to y are continuous at the point a, b, then the conclusion is that capital F is differentiable at the point a, b. And the previous equality is also true. And the derivative of capital F at AB acting on HK will equals this is the same equality as above. Okay, so this is the relationship between the differentiability of capital F and our two partial map F1 and F2. Okay. So we consider the proof of this proposition. The second will be much easier. So dxf is the metric we wrote previously. dxi capital F j I from 1 to m j from 1 to p. This are continuous at AB. This means all these partial derivative function of the components are continuous at AB, and also the partial derivative with respect to y is the matrix d yi fj I from 1 to n j from 1 to p. This continuous at AB means d yifj are continuous at AB. So this means the map, the components of F of our map, the components of this map, I have no place to write. The component of this map are differentiable. Okay, differentiable. Therefore, F is differentiable. Okay. As a map from of x, y. Are differentiable. Because the component function fj has continuous the component function fj has continuous derivatives function which respect to all its variables xi, xy, x2, xm, and y1, y2, yn. So by a previous theorem, we have proved we know that fj is differentiable function of x and y. So the components of capital F are all differentiable. Therefore, the map F itself is differentiable. Okay. So the differentiability of the capital F can be proved in this way quite easily. Okay.